Okay, so we've talked a lot about straight things like lines and planes. What about a curvy surface in 3D? So let's start to talk about that. Okay, so what I want to do is talk a little bit about quadratic surfaces. So in 2 dimensions, there are certain curves that pop up frequently, like a circle. We can talk about parabola. This is less known, but this is hyperbola. A hyperbola might look something like this. Something like that. And let's see, what am I forgetting? Like an ellipse, right? So this might be a formula that you're more used to. So let's see. That would be an equation for ellipse. Now, when it gets to 3 dimensions, we have 3 variables, x, y, and z, and we're throwing in second power, right? So quadratic surfaces. There's a lot, there's a ton. And I don't really want you to waste your brain space memorizing these things. But what I want you to be able to do is to look at an equation, look at a picture, and be able to match them. So some of the techniques that you could use, some kind of quantitative reasoning skills to illuminate, like, oh, this equation has this feature, so it must be this picture and it can't be this picture. So I want you to be able to deduce things like this. And these techniques will come into play later on in the class. So I think it's a good time to practice this. So what I have for you, I have 6 equations and 6 beautifully computer rendered picture of these. I didn't want to draw these by freehand. The tick marks is kind of obscured, but I think that's okay. Don't worry about the constant too much. Let's figure out which would have to match to which. Okay, let's see. So where to start? Well, there's one quadratic surface that you already know, and that's a sphere, right? So actually, let me erase these notes. That's high school algebra 2 stuff that maybe you've seen a while ago. But it'd be good to mention a sphere. Okay, so if you know that this corresponds to a round ball-like shape, that might give you a starting point to figure this out. So there's one picture here that's not quite a sphere, but it's like a squished egg, right? This thing is called ellipsoid. Again, you don't have to memorize these names, but it's kind of good to know that they are names. And some of these sound funky, so maybe you enjoy knowing the name. So this is an ellipsoid. And you might guess that, well, you know, formula for ellipse and circle is similar. So maybe formula for sphere and ellipsoid is similar. And that might be a good place to start. So let's see. I think notice that some of these terms has positive coefficients and negative coefficients, and also noting that it has a constant term, like a sphere has a constant r squared term. You might guess that. I think number one might be ellipsoid. So maybe I will name these pictures in Roman numerals. And that's 6. Okay. So this would be an ellipsoid. That's picture 2. And how else would you be able to figure out if you didn't realize that you knew what the sphere equation was? So another way to kind of determine that kind of distinguish this picture from all the other 5 other pictures is that this is the only picture that fits in a box, right? Every other surface is kind of extending out into infinity. This is the only thing that's kind of bounded, that literally fit in a box. How could you figure this out from the formula? Well, you know that all of these 3 terms has positive coefficient times something squared. And when something is squared, it's either 0 or positive, right? So here we're adding up 3 non-negative things, and it adds up to 36. So that means that none of these things could be too big, right? For example, even if x and z is equal to 0, if you look at 36y squared is equal to 36, the only way that could hold if y squared was is 1, right? Like it can never be greater than 1, because then that term alone will be bigger than 36. So this is the only picture that kind of has that bounded feature. So that might be a good thing to notice. Okay. Another technique that you might use is that you can kind of look at 2 dimensions at a time. So imagine I'm looking at this equation. And looking at 3 different variables at once is difficult, but we are used to looking at 2-dimensional equations. So if z is equal to 0, so z is equal to 0 is the floor. So it's like it's the xy plane of the 3D axis. So if z was equal to 0, this term will drop out. And what we're left with is 9x squared plus 36y squared is equal to 36. And if we divide both sides by 36, maybe you recognize this as an equation of an ellipse. And if you kind of cut this picture, at z equals to 0, you could see that the cross section is an ellipse. So I mean, there's a couple pictures like that. So this one has an elliptic cross section, and this one also looks like it could have an elliptic cross section. So that's not the only picture, but that's one technique that you could use to kind of determine what the cross section looks like. Okay, so I think enough talking about the first picture. Let's see, what else could we look at? Okay. I want to look at this second picture. So here, this guy is called paraboloid. Or actually, it's called elliptic paraboloid. And there's one feature that this one has that no other picture has, which is that it's everything is above a certain point. Right? There's kind of it doesn't go where z is too negative, right? So maybe we can use that to figure something out. Okay. All right. So I'm looking at this equation right here. And the reason why I'm honing on in this is that if I put the 6z on the other side of the equation, notice how the left-hand side is non-negative, right? It's, again, positive coefficients and something squared, which is never negative. So the left-hand side has to be 0 or positive. So the right-hand side has to be 0 or positive. So you can never have a negative z here. And this picture is the only picture that does not have negative part for the z. So this must be it. So this is paraboloid, or elliptic paraboloid. And that's picture number 3. And we could look at the cross section again as well. So if you fix some positive value for z, again, you'll get the cross section will be ellipse. Okay. You could actually look at cross section x and y direction as well. So for example, if you set x equals to 0 here, so then this term will drop out. Then you'll get an equation of a parabola, right? So if x is equal to 0, kind of cross section that cuts this way cuts into a parabolic shape. So that's another way to kind of check your understanding. Look at slices of picture when you fix one of the variable to a constant. Okay. All right, so we figured 2 of them out. Let's see. I think I want to look at this one right here. Okay. So I'm looking at the 4 that's left. So this looks like a cone, right? This thing is called cone. It looks like a traffic cone that's balanced on its tips. So one feature that, so I'm looking at the rest. And I think I'm looking at this one. Okay. Okay, actually, there's 4 that's left, and then there's 4 pictures that are left. So maybe one way to kind of separate them into small, narrow down the choices is to notice that some of these pictures have the origin included in the graph, and some of them don't. So what I mean by origin is the point 0, 0, 0 in the picture. So if you look at this picture, the origin is at the tip of these two cones. And I think that's probably the origin. It looks like parabola going this way and parabola going the other way, but it touches the origin. This one does not touch the origin. It kind of envelopes it from both sides, right? It contains it, but it doesn't touch the origin. And here it also looks like origin is not included. So I'm looking at the four equations that are left. And well, the ones that has constant terms on the right-hand side, if I plug in 0, 0, 0 for x, y, and z, this equation is not satisfied, while equation number 2 and equation number 6 does satisfy a particular value of z, x, y, and z equal to 0. So I think that means that one of these is 1 and the other one is 4 in the picture that I've drawn. Okay. So then we narrowed it down to the equation 2 or equation 6. So I think one way to work this out is that if you fix a z value that's something other than 0, let's say, it looks like 4, if you cut it sideways, sorry, trying to draw it. If you cut it at a certain positive z value, it looks like the cross section is a hyperboloid, okay. Opposed to if you cut it at a certain positive z value, I think the cross section looks like a circle or ellipse. And I think it needs to be an ellipse because of the equations here. So if I fix a z value, let's say z equals to 1, this turns into 4x squared plus 9y squared is equal to 4. And if I mean, this is ellipse, right? If I divide both sides by 4, I get an equation for ellipse. While if I take this picture, equation number 6, and then set z equals to 1, okay, and this is an equation of a hyperbola. Okay. So that must mean the number 2 here is the cone. So that's picture 1. And equation 6 must be this guy. What is this guy called? Let me look it up. This is called the hyperbolic paraboloid. Okay, and this is the picture 4. No, that's a Roman numeral 6. I think that's 4. Okay, so hyperbolic paraboloid. And you can kind of see that because, you know, the cross section had parabolas, and there was also different cross section was hyperbola. So that name is reasonable. Okay, all right. So we're down to two pictures, 5 and 6. Let's see. So there's a couple different ways to go about it. We could use the same techniques that we've been using. So if we fix a z value, it looks like the cross section looks like ellipses in picture 5. And then if we did the same thing here, it would look like a hyperbola for a fixed value of z. Yeah. So maybe that's a way to figure out which one's 3 and which one's 4. Let's see. Yeah, okay. So if we fix, let's just fix the z at 0. So if I plug in 0 for z, it looks like the equation 3 is an ellipse, right? It looks like, equation of a circle except different coefficient, positive coefficient in the front. And one of the signs is flipped on this one. So this looks like a hyperbola for the other one. So this must mean this is 5. And this is a picture 6. And what are these graphs called? So they're both called hyperboloid. But this is called hyperboloid of one sheet. And this is called hyperboloid of 2 sheets. And you might be wondering, hey, where's the hyperbola on picture 5? If you cut it in other directions, you get a hyperbola. So if you kind of cut it vertically like this, you'll get hyperbola that way. And if you also cut it this way, you get a hyperbola that way as well. Okay, so I think we got the mix and match. So again, let me just kind of be clear about the expectations of what you need to know for these things. You don't have to memorize all these formulas and where does the positive and negative signs go for it to be a particular picture. We have technology that could graph these kind of things, but it is still useful. The techniques of like fixing one of the variables to a constant, look at the cross section, and get like understand the two-dimensional picture. That's a really useful idea. And also being able to work out, hey, this equation is kind of bounded, right? Like the ellipsoid was kind of bounded in a box. You should be able to figure that out given enough time to look at the equation. And another key technique that we used was we plugged in a particular value, right? Like we plugged in 0, 0, 0, and either satisfy the equation, which means it's part of the graph, or it doesn't satisfy the equation so that the surface does not touch the origin. So that's a useful thing to test and work out. Okay, I think that's where I want to cut the video. I'll see you later.